Okay, let's try this exercise from the Wallace book. I'll go through it very briefly. The flux density, or Fs, of solar radiation incident upon a horizontal surface at the top of the Earth's atmosphere at 0 zenith angle, that means direct from the top, is 1,368 watts per meter square. Estimate the intensity of solar radiation. Assume that solar radiation is isotropic, which means that every point of the surface of the sun emits radiation with the same intensity in all directions. So for reference, the radius of the sun is Rs is equals to 7 times 10 to the power of 8 meters, and the Earth-Sun distance is d at 1.5 times 10 to the power of 11 meters. That's quite far away from the Earth. So we start this example by using the equation Fs, or the flux density, is equals to the integral of I cos the zenith angle and the fraction from the fraction of the sky. So since I is constant, it comes from all directions, so we can bring that out, and that just leaves us with this. And because we assume that all of the rays of the sun is at 90 degrees from the surface, which means that it is at 0 zenith angle, then we can take this as 1, and it also comes from a single point in the sky, which also makes it reduced to 1. So we can simplify this to just become 1, and that will just leave us with this. Now we want to calculate the solar intensity, and we rearrange the equation to make I the subject, and that leaves us with this d omega, which we need to calculate. Now we have Fs, which is equals to 1,368 watt per meter square. Now we just need to calculate d omega. Now d omega is a fraction of the sky that is the sun, and we can estimate that by using the ratio of the radius of the sun and the distance that the sun is away from the Earth. So dw over 2 pi, which is the entire hemispheric source of the Earth, is equals to the size of the sun, or the area of the sun, pi r square, where rs is the radius of the sun, which is given in the question, over the entire sky, or the entire large area of the sky. So that is can be considered as a hemisphere at 4 pi d square. So basically it's like the Earth is here and the sun is here. This is the distance between the sun and the Earth, and this is the radius of the sun. So the fraction of the sky that's covered by the sun on Earth is just this hemisphere, entire hemisphere, that's covered by the sun in this area. So the entire area of the hemisphere, which is this one, the area of the sun over the entire area of the hemisphere, which is a factor of the fraction of the sky, dw, over 2 pi the hemisphere. So you can calculate dw just by rearranging the equation to become this, and here, oh wait, because it's a hemisphere, so this one should be 2 instead of 4. 4 is for a sphere. Then we can just cancel this out, and that will leave us with this. And now we just need to substitute the value. Rs is 7 times 10 to the power of 8. meter square over d, which is 1.5 times 10 to the power of 11. Calculate this and you'll get 6.84 times 10 to the power of -5. The units of this is the stir radian. Now we just substitute this value back into the above equation, this one, and we get 1368, which is in watts per meter square, divided by 6.84 times 10 to the power of -5, unit of stir radian, and that will just give us approximately 2 times 10 to the power of 7 watt per meter square per stir radian or solid angle. So that is the intensity of the sun for every solid angle